Welcome to the deep dive. Today, we are opening the door to, well, one of the most brilliant and frankly infuriating thought experiments in modern philosophy and cognitive science.
We're talking about the Chinese room.
Exactly. This is the ultimate test for what's called strong artificial intelligence, and our mission today is to explore John Searle's famous argument that a computer, no matter how sophisticated, can't truly think or understand.
That's right. And for you, the curious learner, this deep dive is a shortcut, really, past decades of academic debate. We're going to drill down into the two most radical claims made by the early proponents of strong AI.
Claims that really force us to define what we even mean by mind in the digital age.
So the sources start by drawing a really important line in the sand.
Two definitions of AI, basically. Let's make sure we have the camp straight. First up is weak AI.
And this view is pretty pragmatic. Most people don't have an issue with it.
Right. It just says the computer is a powerful tool. It's fantastic for modeling human processes, for testing hypotheses rigorously, for helping us study the mind. No one's really arguing with weak AI.
But then there's strong AI. And this is the ambitious, defining claim that we're here to challenge today.
This is the big one.
Strong AI asserts that an appropriately programmed computer, well, it literally is a mind.
It doesn't just simulate understanding.
No, it has genuine cognitive states. And crucially, its proponents claim that the programs themselves are the complete explanation for human cognition.
So to be clear, our deep dive is strictly focused on dismantling those two claims of strong AI. First, that the program alone constitutes understanding.
And second, that it explains human cognition. We're really asking whether just shuffling symbols around is enough to create genuine meaning.
Right. Can you get from syntax?
The rules, the grammar, the form.
Semantics, the actual content, the meaning.
That's the whole game.
Okay, so let's unpack this by looking at what convinced the strong AI camp they were on the right track in the first place.
Well, they were pointing to some really impressive early successes in programs that could, simulate incredibly complex human tasks like understanding language.
You're talking about the work of Roger Schenck and his team at Yale.
Exactly. Schenck's team was working on teaching computers to understand stories by giving them what they called scripts.
Scripts?
Yeah, representations of common human experiences, like the going to a restaurant script.
And the success was, you have to admit, pretty compelling. Let's take a classic example from the sources. The program gets a story.
Okay.
A man went into a restaurant, ordered a hamburger. When it arrived, it was burned to a crisp, and the man stormed out angrily without paying or leaving a tip.
Then the machine gets a question. Did the man eat the hamburger?
And the program, using that restaurant script and the negative cues, it correctly infers.
No, he did not.
Now, contrast that with a different story. A man ordered a hamburger, was very pleased with it, and as he left, he gave the waitress a large tip before paying his bill. Same question. Did the man eat the hamburger?
And the answer comes back. Yes.
So it looks like it's demonstrating human-like common sense, right? Like it has a deep understanding of the whole situation.
That's exactly what the strong AI partisans asserted. They claimed that because the machine could do this, it was proof. Proof that A, the machine literally understood the story.
And B, that the program, the script itself, explained how humans do it.
The output was indistinguishable from a human, so the understanding must be there.
And if you just look at the behavior, it's a powerful case. It passes that test. But in philosophy, to test a theory of the mind, you don't always need a lab.
Sometimes you need a thought experiment, like a Dankin experiment.
And that is exactly where John Searle introduces the Chinese room.
The Chinese room is just brilliantly designed to test that core assumption of strong AI, that mind is to brain as program is to hardware.
Okay, walk us through it.
Searle asks us to imagine him, a person who speaks only English, and he's locked inside a room. All by himself. The room has a slot, and through that slot, he receives these large batches of Chinese writing. Could be a script, a story, some questions.
But the critical part is he knows zero Chinese.
Not a single character. To him, they're just meaningless squiggles, just formally defined shapes.
Okay.
But inside the room, he has a massive instruction manual. That's the program written entirely in English, which he understands perfectly.
And the rules tell him what to do.
Exactly. They say things like, when you see squiggles of shape A, followed by squiggles of shape B, go find squiggles of shape X in your databank and hand them out. It's just correlating one set of formal symbols with another.
So he just sits there all day, following English instructions, matching shapes to other shapes, and then sends the results out of the slot. What happens on the outside?
Well, the output he produces is so perfect, so well correlated with the input, that the native Chinese speakers outside the room think you're talking to another native speaker.
To them, the whole system is a fluent, understanding Chinese mind.
Right. But now, here's the moment of truth. Let's pause and think about the man inside that room.
He's executing the program perfectly. He's producing flawless Chinese answers.
But does he understand the stories? Does he know what the questions are asking?
No, of course not.
He understands absolutely nothing. He is merely manipulating, and this is the key phrase, uninterpreted formal symbols.
This is that critical distinction we need to make really clear.
Right. When he's processing the Chinese symbols, all he has is syntax.
Which is just the rules governing the form, the shape, like grammar without any meaning attached.
Precisely. But he has absolutely no semantics. Semantics is the meaning, the content, the connection between that squiggle and the fact that it refers to, say, a hamburger or a restaurant. He has the rules for the shapes, but zero meaning.
But if you gave him the same test in English, he would understand everything. The stories, the questions, all of it.
Of course. But in the Chinese case, even with perfect external output, he understands nothing of the story.
So Searle's conclusion is just devastating for strong AI.
It is. The person in the room who is acting as the program understands nothing of the Chinese. Therefore, the computational process alone, that symbol manipulation, is not enough for genuine understanding.
Okay, but hold on. I have to play the listener's advocate here.
Go for it.
If the man in the room, or the system, produces output that is behaviorally indistinguishable from a native speaker, if it passes the Turing test with flying colors, why shouldn't we just say it understands? You know, if it walks like a duck and talks like a duck.
That's the classic behaviorist challenge, and it's exactly why this whole argument caused such a firestorm. The strong AI camp responded immediately, and their defenses really forced Searle to clarify what he meant by intentionality.
All right, let's get into those rebuttals, because this is where the real battle of ideas happens.
The first major counterpunch was what's called the system's reply, and it often came from the folks at Berkeley.
And their argument was pretty clever. They'd say, the individual man doesn't understand. Sure, we grant you that, but the whole system understands.
Right. The system being the man, plus the rule ledger, the scratch paper, the data banks, the whole apparatus working together.
So the understanding is in the whole complex machine.
But Searle's rebuttal just cuts right through that. He says,
Right.
Let's simplify it. Let the man internalize the entire system. He memorizes every rule, every data bank. He can now do it all in his head.
So he is the entire system.
He is the system. And he still understands zero Chinese. So if he, as the total system, doesn't understand, then the system itself can't understand.
That feels like a knockout. But the sources point out something fascinating here. If the system's reply were true, the implications would just be absurd.
Oh, absolutely would be. If complex information processing in a subsystem is enough for understanding, then what about other complex systems?
Like what?
Well, by that logic, you'd have to say your stomach possesses beliefs about the nutrients it's processing, or that the heart has cognition about pumping blood.
You could even take it to a simple thermostat, right? It has the belief that the room is too cold because it takes input the temperature and produces an output turning on the furnace.
Exactly. A thermostat with beliefs. The whole concept of mind becomes meaningless. We want to explain what's unique about cognition. And strong AI ends up saying everything that processes information is a mind. It explains nothing.
So the system's reply fails because it confuses computation with consciousness.
Which leads directly to the next defense.
This one is the robot reply from Yale, I think.
That's right. And it tries to tackle the abstract, symbolic nature of the Chinese room. The claim was, look, the thought experiment is unfair because real intelligence is embodied. It interacts with the world.
So what if we put the computer inside a robot? Give it a TV camera to see and arms and legs to act. Now it has real causal connections to the outside world. Surely that system would understand.
Let's run the experiment again.
Yeah.
We put our monolingual English speaker inside the robot's head as a little homunculus.
The man in the machine.
He's still just getting streams of formal symbols from the camera and sending out streams of formal symbols to the motors, all based on his English rulebook.
He has no idea that the incoming symbols mean red apple or that the outgoing ones mean pick it up.
None whatsoever. He's just manipulating shapes. The robot moves around, but the man inside still lacks any intentional states about what's happening. No beliefs, no desires, no actual understanding of his environment.
So the robot is just an ingenious mechanical dummy adding a body doesn't solve the core problem. You still haven't bridged the gap from syntax to semantics.
And that takes us to the final and probably most complex defense, the brain stimulator reply from folks at Berkeley and MIT.
This one always felt like a bit of a retreat for strong AI.
It is, because it starts to hint that maybe the neurobiology does matter. The idea is, what if we simulate the actual sequence of neuron firings at the synapses of a native Chinese speaker's brain? Surely that has to produce understanding.
So we model the formal electrical structure of a thinking brain. Does that replicate the thought?
And the answer is still no. Searle uses this great water pipe analogy. Imagine the man in the room isn't flipping through a book anymore.
Okay.
Now he's standing in front of this incredibly elaborate network of water pipes with valves and faucets. Each connection corresponds exactly to a synapse firing in the Chinese brain.
So Chinese input comes in, and his English instructions say, turn valve 4, then open faucet 7, which simulates the neuron firings, and a Chinese answer pops out the other end.
The simulation is perfect at a formal, structural level. But the man doesn't understand Chinese, and the water pipes certainly don't understand Chinese.
So what's the flaw here? This seems like the closest you could get.
The flaw, which all the replies miss, is that the simulation is of the wrong thing.
Wait, run that back for us. How is simulating the brain's structure the wrong thing?
Because they're only simulating the formal shadow, the abstract pattern of the firings, not the actual causal properties of the biological brain tissue itself. A formal description of an electrical pulse in a silicon chip is just not the same thing as the specific neurobiological process that gives rise to consciousness and intentionality in our brains. The software is not enough.
And this brings us right to the heart of Searle's entire critique. Strong AI is making a fundamental error.
It's confusing simulation with duplication.
The analogy in the sources is so clear on this. No one expects a computer simulation of a 5-alarm fire to actually burn the neighborhood down.
Or a simulation of a rainstorm to get you wet. Simulation is not the same as the real thing.
So why on earth did strong AI proponents insist that a computer's simulation of understanding must actually understand?
Because deep down, it requires you to believe in a strong form of philosophical dualism. This idea that the mind is somehow separate from the brain's physical, messy chemical properties. It relies on that broken equation. Mind is to brain as program is to hardware.
And the fatal flaw in that equation is that the program's independence from the hardware, the very thing strong AI celebrated, is actually what kills the whole argument.
Exactly. Because intentionality, meaning understanding, having beliefs about something, is a biological phenomenon.
Just like lactation or photosynthesis.
Or digestion. It is causally dependent on the specific chemical and physical structure of the brain. The stuff matters.
So the hardware must matter.
It absolutely must. If a program is hardware independent, it means you can run the same program on anything. You could run it on a system of water pipes, wind machines, or, as Searle famously suggested, toilet paper and small stones.
And none of those things have the right causal powers to produce genuine understanding.
They can't. The program is purely formal. It only has syntax. Intentional states are not formal. They are defined by their content, by their semantics.
So if we go back to the core philosophical questions that started this whole thing, we actually have some clear answers now based on this argument.
Could a machine think?
Yes, we are those machines. Humans are biological machines that think.
Could an artifact think?
Yes, in principle. If we built it out of the right stuff, that could duplicate the necessary causal powers of the brain.
But here's the crucial one. Could something think solely by virtue of running the right program? Could a program by itself be a sufficient condition for understanding?
And the answer from the Chinese room is a definitive no. Formal symbol manipulation just doesn't have semantics.
This whole argument really shows why the famous Turing test, which only looks at behavioral input and output, is ultimately not enough.
It's a deeply behavioristic test.
It is. You can pass the test, just like the man in the room does, without a single shred of real understanding.
If strong AI were right, then whatever our brains are doing biologically to produce minds would have to be irrelevant. But if our minds are tied to our biology, then any theory that ignores the causal power of the brain is confusing the formal shadow with the conscious reality.
So we'll leave you with a final thought, and it's especially relevant today with large language models generating such fluent and compelling text. If we eventually build a machine that acts and converses in a way that is totally indistinguishable from a thinking human, it passes every behavioral test you can throw at it, are we forced to accept that it genuinely understands? Or Would knowing its process is still just manipulating billions of uninterpreted symbols stop us from granting it a mind? What evidence, beyond just behavior, would ever count as proof of genuine understanding?
That's a question for you to explore until our next deep dive.